Hello, everyone. It's Mr. Caudell. I hope you're doing well. I'm. We made it this far. Oh, we're almost done. Today, my only goal of this recording is to help you with the final formula in our AP Biology formulas and equations sheet. You don't need this sheet. I'm going to show you what the formula is in just a second. It's this one over here, but you can pull it out and follow along if you'd like, because we've done that all year. Be proud of what you've done as far as learning all this math and all these content areas, and we did all the labs. I feel great about what you did this year. It was extraordinarily hard. I've seen students longitudinally, year to year, for 20 years, and I think this year was by far the hardest. So give yourself a pat on the back, get out a blank piece of paper, because the question is, how many times can you fold a blank piece of paper in half?
How many times can you fold a piece of paper? Assume that one had a piece of paper that was very fine, like the kind they typically use to print the Bible. In reality, it seems like a piece of silk. To clarify these ideas, let's say you have a paper that's 1,000th of a centimeter in thickness. That is 10 to the power minus 3 centimeters, which equals 0.001 centimeters. Let's also assume that you have a big piece of paper, like a page out of the newspaper. Now, we begin to fold it in half. How many times do you think it could be folded like that? And another question. If you could fold the paper over and over as many times as you wish, say 30 times, what would you imagine the thickness of the paper would be then? Before you move on, I encourage you to actually think about a possible answer to this question. Okay, after we have folded the paper once, it is now 2,000ths of a centimeter in thickness. If we fold it in half once again, the paper will become 4,000ths of a centimeter. With every fold we make, the paper doubles in thickness. And if we continue to fold it again and again, always in half, we would confront the following situation after 10 folds. 2 to the power of 10, meaning that you multiply 2 by itself 10 times, is 1,024 thousandths of a centimeter, which is a little bit over 1 centimeter. Assume we continue folding the paper in half. What would happen then? If we fold it 17 times, we'll get a thickness of 2 to the power of 17, which is 131 centimeters, and that equals just over 4 feet. If we were able to fold it 25 times, then we would get 2 to the power 25, which is 33,554 centimeters, just over 1,100 feet. That would make it almost as tall as the Empire State Building. It's worthwhile to stop here and reflect for a moment. Folding a paper in half, even a paper as fine as that of the Bible, 25 times would give us a paper almost a quarter of a mile. What do we learn? This type of growth is called exponential growth. And as you see, just by folding a paper, we can go very far, but very fast too. Summarize, if you fold the paper 25 times, the thickness is almost a quarter of a mile. 30 times, the thickness reaches 6.5 miles, which is about the average height that planes fly. 40 times, the thickness is nearly 7,000 miles, or the average GPS satellite's orbit. 48 times, the thickness is way over 1 million miles. Now, if you think that the distance between the Earth and the Moon is less than 250,000 miles, then starting with a piece of Bible paper and folding it 45 times, we get to the Moon. And if we double it one more time, we get down to Earth.
Isn't growth incredible? We have to talk about growth, and that's what this formula deals with. Because growth is important in any population, whether it has a positive or negative growth aspect to it, or I guess the way that it's growing. Exponential growth is especially crazy. The thing what they don't show in that is that what would happen if you start to get to like 30 folds, 40 folds, that thing would become super, super narrow, like a toothpick or the width of a hair, for instance, or much thinner than that. So the only way that it gets that tall is if it gets that small or narrow. But exponential stuff is pretty cool. The exponential model describes the population growth in an idealized, unlimited environment. If you flip over your AP Biology formulas and equations page, you'll see this formula way up there in the top left corner. We haven't talked about any of this yet, but it's kind of commonsensical. Let's take a look. Let's take a moment and look at these algebraic terms here. So I'm just looking at the screen. We've got the amount of change up in the upper right corner there. There's time, birth, death rates. The N is the population size, K is carrying capacity, and this R is some sort of growth rate of a population. Now there could be a maximum one that will give you exponential growth, but there are other times when it's not maximum. If you look over on the left side, you'll see 4 formulas, and basically you're just going to plug and chug numbers that they give you on the AP exam into those formulas, and then get some sort of growth or rate. I guess rate is the first one. It's pretty easy, I think. So let's just go through this. I had you watch a movie on bunnies now twice, and all of these concepts are gone over here. And what I like about this movie too is that they also talk about some of the reasons for density dependent and density independent growth in populations. There are things like resource availability or waste buildup or space or things like that is the reason why we don't have bunnies that cover the earth, essentially. Well, the first thing that we'll go over is exponential growth. Now, what's interesting is that anything in biology grows in an exponential fashion. Once it gets into a new area, there's enough resources for it, anything does. But that obviously is always slowed. Like, you can even think of like a bacteria. Or a COVID-19 virus. If it gets inside of, let's say, a receptive human, it finds that there's usually space and resources and all these things, and it can start to grow. But the problem is that it runs out of stuff after a while, and then this growth rate starts to kind of turn over, and it becomes, rather than a J-shaped curve, it becomes an S-shaped curve. But when we deal with exponential growth, which happens in any population at the beginning, it's going to have a change in population over time. That's what the delta N time over delta T is. So how does the population change over time? And the way that is figured out is that you just do the growth rate, which is little r, times the number of individuals in your population. And they did that in the bunny movie. These conditions, the rate of reproduction is definitely at its maximum. This is what was happening with the COVID-19 virus.
Basically, we have to talk about population growth. And so any population where you have a positive R, and R stands for growth rate. If you ever have a positive R, you're going to follow a curve that looks kind of like this. You'll first of all have exponential growth, and then eventually you'll run out of space or food. There's going to be competition, and eventually you're going to hit what's called logistic growth. And so we call this the J-shaped curve, the exponential, or the sigmoidal or the S-shaped curve, which is logarithmic. And so what is N? N is going to be the number of individuals in the population. And so right here, if we put N on this side and we put time on the x-axis, as time goes on, the numbers are going to increase. So this would be a low N value right here, and this would be a higher N value, and this would be a really high N value. And so it's important that you know what N is. That's the number of the population. R is the growth rate. Remember, if it's ever positive, and how do we calculate growth rate? It's basically the number of people being born minus the number of people who die. If we ever have a positive one, then we're going to get this curve. Now, it's not always radical like this. Sometimes it's going to be really gradual like this. Sometimes it's going to be incredibly quick, depending on what the R value is. And then the last thing is K. K stands for carrying. Let's try to spell that right. Capacity. So basically that means in an area for a certain group of a certain population, there's like a maximum amount that they can support. So we call that the carrying capacity, and that's where the limit is. It's eventually going to level out on that. And so if I were to talk about in the real world, because this is just a math formula, basically in the real world, we put wolves back in Yellowstone Park, and so there was tons of food there, not a lot of competition, and so basically their growth rate went up. And then it's dropped, and it's gone up, and it's dropped, and it's kind of reached this carrying capacity, a maximum number of wolves you can have in Yellowstone Park. And so it's not as smooth as that, but it certainly has an R value, an N value has increased, and then it's reached kind of a K. So it's important that you know what N, R, and K are.
Okay, so let's get to a few examples here. So I went down by the dance room, wrestling room, and I took some pictures of some of the old, I forgot what they, freezes, I don't know what they call these, of the past students here at Battle Mountain High School, your contemporaries, or your counterparts that went through these halls, but actually this was in Minturn when they had this school at the old rummage sale building before Eagle Vale even. And if you notice here in 1961, there were 14 kids, right? So then the question becomes, what happened between 1961 and 1962? And if you look here, now there's 14 kids. That's 3 times 6 is 18. So there were 14 kids. Now there's 18 kids. So the question is, by how much did Battle Mountain grow? And you might say, oh, 4 students. Okay, great. But let me move the computer. But the question is, what's the growth rate? So we had 14 kids, and then we added 4 more. We have 4 more immigrate than emigrate, I guess, over that year. And if you do this, I think it comes out to something like 0.28. I have a calculator over there. Let's look at what happens between 1962 and 1963. I guess you're going to just have to trust me on this. We then get 18 students, and so if we have 4 more students that year from the previous year, we get another number. And so I'm not going to show you these numbers because I've already done this in my head. But the average of these is 0.22. So the point that I'm trying to make here is that we can calculate R. We can figure out what the growth rate is. What's the growth rate? It's 0.22. Then what we could do is we can multiply that times, if we wanted to, we can multiply that times the number of individuals in a population in order to get the change in the population over time. So earlier, so let's go here. Earlier, we saw a lot of graphs, so I'm going to draw a line on this graph here, and we're going to, like I said, always make it logistic in growth, which is this J-shaped exponential curve. And that's what happens until it reaches some sort of, I'm going to just put a dotted line up here, carrying capacity. And this is abbreviated as K. And so this is K right here, the carrying capacity, whatever that number may be. And then eventually what's going to happen is that this is going to slow down. Often the exponential growth goes above the carrying capacity, and then there's a lot of pain and suffering and death. And then it will often overcorrect underneath it, but then it will see an opportunity there because now there's less individuals than the environment can carry. And so it often goes like this, but that averages over time to be a straight line. We'll get to that map in just one second. But to give you an example right now, there are many people who think that the Earth is at its carrying capacity. We've hit the amount of people or gone over the amount of people that our Earth can sustain. And so we've had this terrible virus, COVID-19, that has come along. And some people would say, hey, that's one of nature's checks and balances. We've gone over our number of individuals that we can sustain on this planet, and then we're checking that, or nature is checking that. Now that's cruel. It's a cruel way to think. But I guess maybe some population ecologists might think that way. So let's read this. This is a 53.3 concept check question number 3. It says in 2006, the U.S. had a population of about 300 million people. If there were 14 births and 8 deaths per 1,000 people, what was the country's net population growth that year? So if you do this math, if you see So if there's some births and some deaths, let's do that over 1,000. So let's do 14 over 1,000. That's 0.014. And then 8 deaths per 1,000 is going to be 0.018. So if I subtract 0.008 from 0.014, just the birth and the deaths per 1,000 people, I get 0.006. So that's basically the growth rate is 0.006, I guess, per 1,000 people per year in 2006. Then if we multiply that times 300 million, so let me just do times, I get 1.8 million. So the question is, what was the country's net population growth that year? 1.8 million people. Do you think the U.S. is currently experiencing exponential population growth? Probably not, for sure, due to lack of resources. We're just not doubling like every year. If you want to, you can press pause and take a look. This is the book's way to answer this question. Oh, there it is, misplaced. You tell I'm a little bit out of practice. So let's take a moment. I'm gonna stop talking. Go ahead and compare these two growth lines and their growth rate, please. You can see that the blue line is half of the growth rate as the red line, and that the curve is definitely less steep on the blue line, the second one there. So here's the final concept here on this formulas and equation sheet, logistic growth. It describes how a population grows more slowly as it nears its carrying capacity. We saw this in the movie. You can go back there if you'd like. Also, the logistic model has a carrying capacity, which is the maximum population size the environment can support.
Bacteria introduced into an environment abundant in needed resources grow in a specific manner. Initially, individual bacteria are still maturing and are not yet able to divide. This is termed the lag phase and can last from hours to days. During this time, bacteria are producing whatever proteins are necessary to live within the new environment. Replication starts and rapidly continues during the second phase, termed the log, or logarithmic, or exponential phase. Bacterial cells undergo binary fission at a constant rate, and thus the number of bacteria increases logarithmically. That is, one bacterium divides into 2, which replicate into 4, which then produce 8, and each individual bacterium in the process replicates at a constant rate. As the bacterial population continues to grow, the nutrients are used up, and waste products from the bacteria build up in the environment. The loss of nutrients and buildup of waste products can cause the environmental pH or temperature to shift, which in turn makes the environment a less optimal growth area for the bacteria.
So here's the last thing I'd like you to do. Go ahead and write down this formula for the logistic growth model. And the only difference here between this and the exponential model is that it has like another factor here at the far right side. K minus N over K. So often they're going to tell you a number for K, which is the carrying capacity, and you can tell right away here that if we're growing at an exponential rate, that's fine, and then we multiply it times some number that we get here, that's going to influence the ability of this curve to remain steep. So if the carrying capacity is over the population, so if you can see that K, the carrying capacity, is over what the population is at that time, so the population size is less than the carrying capacity, and then you divide that by the carrying capacity, you can see here that there's going to be some sort of factor that you're going to multiply times this stuff, and it's going to affect the curve. But the curve will still be positive. But what you can see also by looking at this is that if the number in the population is over the carrying capacity, meaning if the line is way up here over the carrying capacity, then this is going to be a negative number. What do you think it's going to do to this? It's going to reduce, I guess it's just going to cause this to be negative growth. And that's where you're going to see this, where the line comes down. That makes sense. We'll do a problem. Here's one out of your book on page 1194, using the logistic equation to model population growth. So let's just do question 1 here, and let's use 1,600 as our population size and 1,500 as the or carrying capacity. You can just use the growth rate as 1 because what's happening here is that we have an exponential growth at 1. We've now gone over the carrying capacity, which was at 1,500, because now our population is at 1,600. So what do you predict is going to happen here? And then do the math, please. Well, when you plug all that in, you do get a number that over time, we're going to lose 106 individuals. I guess that's our new growth rate, which is a negative growth rate over time. I hope this was helpful. Make sure that you take a look at these formulas. Make sure you know how to plug and chug them. Thanks for your attention.